So let's start. Number 1. Superfluid helium climbs out of containers. Take helium. Cool it down to about 2 degrees above absolute zero, and it transforms into something called a superfluid. Superfluids have zero viscosity, meaning they flow without any resistance whatsoever. You pour regular helium into a cup, it stays there like any normal liquid. You pour superfluid helium into a cup, and it crawls up the walls, flows over the rim, and drips down the outside until the container is completely empty. The liquid defies gravity, flowing upward against the force that keeps oceans on the planet. The mechanism involves quantum mechanics and something called the fountain effect, where the fluid forms an impossibly thin film along any surface it touches, then uses that film as a highway to escape confinement. The layer is only 30 atoms thick, but it's enough. Superfluid helium can also flow through materials that would block regular liquids, seeping through microscopic pores like a ghost passing through walls. If you try to stir it, your spoon passes through without resistance, like stirring air. The atoms move in perfect synchronization, a collective quantum state where individual particles lose their identity and behave as one unified entity. You can't trap it, you can't contain it, and watching it flow is like watching the laws of physics take a coffee break. Number 2. The Leidenfrost effect lets water droplets dance on lava. Drop water on a surface hotter than 379 degrees Fahrenheit, and something strange happens. The water doesn't instantly evaporate. Instead, it forms a perfect sphere and floats above the surface, skating around like a mercury bead. The bottom layer vaporizes so quickly that it creates a cushion of steam, and the droplet levitates on this vapor barrier, insulated from the extreme heat below. This is the Leidenfrost effect, and it gets absolutely ridiculous at extreme temperatures. Pour liquid nitrogen on your hand, and it won't freeze your skin off instantly because the same effect creates a protective barrier. Scientists have filmed water droplets dancing on surfaces heated to 700 degrees, even on molten metal, gliding around in seemingly impossible defiance of heat transfer. The droplet can last for minutes, skating in lazy circles while surrounded by temperatures that should vaporize it in milliseconds. You can even walk barefoot across red-hot coals using this principle, your sweat creating momentary vapor barriers with each step. The effect breaks down eventually. The droplet shrinks as it slowly evaporates. But watching a sphere of water casually rolling across lava looks like video editing, not physics. Number 3. Non-Newtonian fluids act like solids when you hit them. Mix cornstarch and water in the right ratio, and you create a substance that cannot decide what state of matter it wants to be. Pour it slowly, and it flows like liquid, dripping through your fingers in lazy streams. Punch it hard, and your fist bounces off a solid surface. This is a non-Newtonian fluid, and it responds to stress in ways that violate every instinct you have about how liquids behave. The faster you apply force, the more solid it becomes. People have filled swimming pools with this mixture and walked across the surface, their weight distributed quickly enough that the fluid turns rigid beneath their feet. Stop moving, and you sink. The particles inside are tiny, irregular shapes that flow past each other easily under gentle pressure, but jam together into rigid structures when force hits them suddenly. Some non-Newtonian fluids work in reverse, becoming more liquid under stress, like ketchup that won't pour until you shake or hit the bottle. Quicksand is a naturally occurring non-Newtonian fluid, and struggling makes it grip tighter, the violent motion causing the sand and water mixture to solidify around your limbs. Silly putty is another example, bouncing like a ball when thrown, but tearing like taffy when pulled slowly. These substances occupy a twilight zone between solid and liquid, their properties shifting based on how you interact with them, and watching them respond feels like the universe is trolling our expectations. Number 4. Magnetic liquids form impossible spikes. Ferrofluids are liquids laced with nanoscale magnetic particles, and they respond to magnetic fields in ways that make them look alive. Bring a magnet near ferrofluid, and the liquid erupts into sharp spikes, perfect geometric peaks that stand rigid despite being made entirely of liquid. The spikes form because the magnetic particles align with field lines, creating a structure stiff enough to resist gravity and surface tension. Move the magnet and the spikes follow, tilting and stretching like the fluid is tracking the magnetic source. The effect is purely magnetic, no chemical reaction, no heat, just liquid iron particles organizing themselves into impossible architecture. Scientists have created ferrofluid sculptures that respond to music, the magnetic field modulated by sound waves, causing the spikes to pulse and dance in rhythm. The fluid looks like something from a science fiction movie, like sentient liquid metal forming weapons or tendrils. In reality, ferrofluids are used in speakers to dampen vibrations and in hard drives to create frictionless seals, but watching them respond to magnetism makes them seem paranormal. The spikes can grow several inches tall, perfectly symmetrical formations that hold their shape until the magnetic field weakens. Then they collapse back into liquid in an instant, the structure vanishing as if it never existed, leaving only a smooth, magnetic puddle. Number 5. Laminar flow makes water look frozen. Turn on a faucet at precisely the right flow rate with minimal turbulence, and water streams out in what looks like a solid glass rod. This is laminar flow, where liquid moves in parallel layers with no mixing between them. The stream looks so perfectly smooth and motionless that your brain interprets it as a solid object. You can touch it and feel water flowing, but your eyes insist it's frozen. The effect requires careful control, each layer of fluid sliding past its neighbors without creating eddies or vortices. Any disruption causes the flow to break into turbulent chaos, but maintain the conditions and you can create streams that look computer-generated. Scientists use laminar flow in microfluidics, where liquids flow through channels thinner than human hair, mixing only where intended. The Reynolds number, a ratio of inertial forces to viscous forces, determines whether flow is laminar or turbulent, and getting it low enough requires either high viscosity, slow speed, or narrow channels. Honey flows in laminar patterns more easily than water because it's thicker, resisting the chaotic swirls that break up clean flow. You can film water in laminar flow, vibrating at specific frequencies, and it appears to freeze midair, flowing backward, or floating in defiance of time. The stroboscopic effect syncing with the camera's frame rate to create impossible motion. Number 6. Supercooled water stays liquid below freezing. Cool water slowly and carefully, removing all impurities and vibrations, and you can drop it below 32 degrees Fahrenheit without it freezing. Supercooled water exists in a metastable state, liquid despite being colder than ice. The molecules want to crystallize, but need a nucleation point, a tiny imperfection or particle around which ice crystals can form. Without that trigger, the water stays liquid, waiting. Touch it, shake the container, or drop in a single ice crystal, and the entire volume freezes almost instantaneously, ice spreading through the liquid in visible waves. You can pour supercooled water and watch it turn to slush midstream, the disturbance providing enough nucleation sites to trigger crystallization. The effect is common in clouds, where water droplets remain liquid at temperatures well below freezing, creating supercooled rain that freezes on contact with any surface. This causes ice storms, where trees, power lines, and roads become coated in thick layers of ice within minutes. Aircraft flying through supercooled clouds accumulate ice on their wings, the impact of droplets providing the disturbance needed to freeze them instantly. You can create supercooled water at home by placing purified water in a smooth container in your freezer, then tapping it sharply to watch crystallization race through the bottle. The phase transition releases heat, the paradox of water warming up as it freezes, and watching liquid turn solid in seconds feels like controlling physics with your fingertip. Number 7. Quantum locking suspends objects in midair. Take a superconductor, cool it with liquid nitrogen, and place it near a magnet. The superconductor locks into position and hovers, resisting any attempt to move it. Push it, and it returns to its exact position. Tilt it, and it maintains the same angle. This is quantum locking, also called flux pinning, and it looks like levitation pulled from special effects. The superconductor traps magnetic field lines in place, creating invisible rails that hold it in three-dimensional space. You can flip the magnet upside down, and the superconductor hangs beneath it, defying gravity without support. The effect is strong enough to suspend significant weight, and demonstrations show superconductors racing around magnetic tracks at high speeds without touching the surface. Quantum locking occurs because superconductors expel magnetic fields when cooled below their critical temperature, a phenomenon called the Meissner effect. But small imperfections in the superconductor trap some field lines, pinning them in place and creating the locked, hovering effect. The superconductor can slide along field lines, but resists moving perpendicular to them, allowing it to glide on magnetic tracks like a frictionless train. Scientists are developing transportation systems based on this principle, magnetic levitation trains that float above tracks with zero friction, limited only by air resistance. Watching a disk of superconductor hover motionless above a magnet, resisting gravity and any applied force, makes magnetism look like magic instead of fundamental physics. Number 8. The Mpemba effect. Hot water freezes faster than cold. Pour 2 identical containers of water into your freezer, one hot and one cold. Logic says the cold water should freeze first because it has less heat to lose. Sometimes the hot water freezes faster. This is the Mpemba effect, named after a Tanzanian student who noticed it while making ice cream in the 1960s. Scientists have confirmed the phenomenon, but still argue about why it happens. Competing explanations involve evaporation reducing the volume of hot water, convection currents distributing cold more effectively, dissolved gases escaping from heated water, or supercooling affecting cold water differently. Some experiments show the effect, others don't, and the conditions required remain frustratingly inconsistent. The phenomenon was documented by Aristotle, Francis Bacon, and René Descartes, so it's been confusing people for centuries. Recent studies suggest hydrogen bonds in hot water adopt different configurations that allow faster crystallization, but the debate continues. The effect is weak and unreliable, but the fact that it happens at all violates the straightforward thermodynamics most people assume governs freezing. You can't depend on it to make ice faster for your drinks. But knowing that temperature doesn't always behave predictably adds another layer of weirdness to something as simple as freezing water. The phenomenon reminds us that even everyday substances hide complexities that science hasn't fully cracked. Number 9. Superfluorescence makes atoms glow in perfect sync. Excite a group of atoms with a laser, and they typically release light randomly, each atom emitting photons at slightly different times. Under specific conditions, the atoms synchronize and release all their energy in a single, brilliant flash, a pulse of light thousands of times brighter than normal fluorescence. This is superfluorescence, a collective quantum phenomenon where atoms communicate through electromagnetic fields and coordinate their emission timing with precision measured in nanoseconds. The atoms act like an orchestra hitting a single, perfect note together, instead of individual musicians playing out of sync. The effect requires dense atomic clouds and precise excitation. But when it happens, the light pulse is so intense and brief that it can be used for precision measurements and quantum computing. The atoms don't just emit light, they emit coherent light, photons marching in lockstep like a laser without the mirrors. Superfluorescence was predicted theoretically decades before scientists could create the conditions to observe it, and watching it occur confirms quantum mechanics predictions about how matter behaves at fundamental scales. The flash happens once and cannot repeat without re-exciting the atoms, making it a one-shot phenomenon. Researchers are exploring superfluorescence in materials ranging from gases to quantum dots, and the effect has applications in creating ultra-precise optical clocks and quantum sensors. Watching atoms decide to glow together, coordinating across space through quantum entanglement, makes individual particles look less like isolated objects and more like connected parts of a unified system. Number 10. Stable liquid columns hang upside down. Flip a bottle of water upside down and it pours out. Obvious. Fill a tube with water, seal both ends, flip it upside down, then carefully open the bottom cap underwater, and you can create a column of liquid suspended upside down, hanging from the top seal with nothing supporting it from below. The water stays in the tube, defying the gravity that should pull it down, held in place by surface tension and atmospheric pressure. The effect works because air pressure pushing up on the bottom of the water column equals the weight of the water trying to fall, creating equilibrium. Break the seal at the top and air rushes in, collapsing the column instantly. The phenomenon is related to how drinking straws work and why you can cover a straw full of liquid with your finger and lift it without the liquid falling out. Tall trees use a similar principle to pull water from roots to leaves, creating continuous columns of liquid pulled upward by evaporation at the top, with the water column held together by cohesion and prevented from collapsing by surface tension. The columns can be surprisingly long, limited primarily by the strength of molecular bonds holding water molecules together. Scientists have created inverted liquid columns over 1 meter tall, massive amounts of water hanging from a sealed top with nothing beneath but air pressure. The setup looks impossible, like paused footage of pouring, and demonstrates how atmospheric pressure is strong enough to support significant weight through sheer persistence. Number 11. The uncertainty beneath the familiar. These phenomena share a common thread. They exist at the boundaries where our everyday intuition about physics breaks down, where quantum mechanics intrudes into the visible world, where temperature and pressure create conditions that transform familiar substances into alien forms. We build mental models of how matter behaves based on what we experience daily. Water pours down, liquids flow smoothly, hot things cool predictably. Then nature reveals exceptions, edge cases where the rules shift. These aren't violations of physics, but demonstrations of how much complexity hides beneath simple surfaces. The universe operates on principles far stranger than our monkey brains evolved to comprehend, and every generation of scientists uncovers new behaviors that challenge assumptions about what matter can do. Some of these effects remained theoretical for decades until technology advanced enough to observe them. Others were discovered by accident, noticed by careful observers who questioned why something looked wrong. The natural world is weirder than most people realize, filled with phenomena that seem like glitches, but are actually features, emergent behaviors arising from fundamental laws interacting in unexpected ways. Number 12. When physics gets personal. What unsettles me about these phenomena is how they make the familiar seem unreliable. You think you understand water, and then it climbs out of containers or freezes faster when heated. You assume liquids flow and solids stay rigid, and then non-Newtonian fluids blur the distinction. These aren't distant cosmic mysteries happening billions of light years away. They occur in laboratories, in your freezer, in phenomena you can recreate at home with cornstarch and patience. The universe is stranger at every scale, from quantum particles to galaxy clusters, and the middle ground where humans exist is no exception. We just don't notice because these edge cases require specific conditions, precise temperatures or pressures or compositions that don't occur in everyday life. But they're possible, they're real, and they're reminders that the physical world operates on rules far more complex and bizarre than the simplified versions we teach in high school. Nature isn't impossible, but it's far weirder than it has any right to be. And the more we learn, the more exceptions we find to the rules we thought were absolute. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.